Good morning, folks. Happy Monday. I have another problem for our playlist here, which I think might be helpful to some of you. So let's go through this one and see how it works. Here we have block B resting on top of block A, which is in turn on top of a horizontal tabletop, as you can see in the picture below. We're told the mass of block B as well as block A. And we're also told that there's no friction between block A and the tabletop, but there is static friction between block A and block B, and the coefficient of static friction is this value here. Additionally, there's this light string that's attached to block A, and it passes over this pulley attached to block C on the other end. And what we need to do is use our Newton's laws tools to find the largest mass that block C can have, so that when we release the system from rest, they will move together kind of like this. And thankfully there's nothing crazy happening in this problem that requires any kind of extensive setup, kind of like that Mars problem we did previously, if you happen to see that one. So we are free to jump directly into the free body diagram for block A. Let's first label the axes of our coordinate system. And I'm going to do mine off to the side so that I have some room to label some stuff in the middle here. But you feel free to label it however you like. Just make sure you're consistent with how you do it. Next, I will superimpose some axes on our highlighted block here. And remember, we are only interested in labeling forces that are acting on block A. Just a reminder. The easiest force to start with, in my opinion, is always weight. So let's include the force of block A's weight, which pulls directly downward. There's a bit of a trick kind of buried in the problem here, in that we have another downward force we have to account for. And that's due to block B pushing down on block A from block A's point of view. And I'm going to represent that as the normal force of block B pushing down on block A with this here. In the opposite direction, we have the normal force of the table that supports both of the blocks. So it's important that you draw the length of it long enough to indicate that it's the sum of these two here. That way, the block remains at a level surface as it slides across, just as we want. And that's it for the vertical direction. We are free to move on to the horizontal. And the first one is pretty obvious. There's this wire sticking out of the block, so let's begin with the tension, which points to the right. And we know that there is static friction from block B acting on block A2, and that it has to act in the direction opposite to the direction that the blocks are moving in. And so since the blocks are moving to the right, this static frictional force has to point to the left. And one other thing we can include here before finishing up block A is the acceleration, which also points to the right, kind of showing the net motion of the way the blocks are moving. And that's it. We're free to move on to block B. So what about this block? Well, we do the same process, starting by imposing those axes. That's not really all that different. We can also start with block B's weight. That will point directly down. Also pretty obvious. But perhaps not so obvious is the normal force now for block B. We have block A, from block B's perspective, now pushing up on block B, preventing it from, falling through the table. So we can represent this as the normal force of block A pushing up on block B. And this is going to be the um, uh, equal and opposite vector to the normal force of B acting on A, as we'll see in a little bit here. And that's it for the vertical direction for block B. What about in the horizontal direction? Well, again, we have to invoke Newton's third law because there has to be some force pointing to the right that's responsible for making block B move along with block A as it gets pulled. Yeah, the only proper direction is also to the right, which would indicate that the acceleration for block B also points to the right as well. And that's it for this block. We don't have any other forces going on here, so there's one last one we have to work on here, and this one is pretty easy. We slap on the axes, and then include our vector pointing down for the weight, of course. And in the opposite direction for block C, we'll have the tension, whose length is smaller than the weight of block C, because we want the block to fall. So, the weight of block C has to be larger than the tension. So make sure you indicate that visually. This will mean that the acceleration vector for block C will point down 2. And at this point, we are done with all the free body diagrams. We can move on to the sum of forces. So let's do that with block A. And I'm going to start off with the vector equation of F equals ma at the top, like we've always done before. And let's branch off into the sum of forces in the x direction, where we have tension pointing in the plus x direction, so it's positive, and static friction from block B acting on block A, pointing in the left direction, so it's negative here on the left. And since the acceleration points in the plus x direction as well, ma is positive. Let's see, what can we do here? Well, we can exchange the static frictional force for mu sub s, the coefficient of static friction, times a normal force, and the normal force here will specifically be the normal force of B acting on A. However, we don't know that yet. We'll end up getting that a bit later. So for now, let's switch to the vertical part of this expression for block A, where we have, like I said before, the normal force of block A minus the sum of these two being equal to 0, which allows us to do the following. We can just solve for the normal force of A, but unfortunately it's not very helpful here. What we need is the normal force of B acting on A. We don't really care too much about what this is. In fact, we don't even know what it is. If you felt inclined to solve for this, and you plugged it in over here, I think you would only be causing yourself a little bit more confusion. So, although this is nice, it's not very helpful. Let's perhaps underline this expression for the time being and move on to the next block and try to find something we can come back to work on this with. So, moving on to block B. This one is fairly easy. Again, we start off with F equals ma at the top, and we do the sum of forces in the x direction first. Here we only have the static frictional force acting in the x direction, and that is equal to ma. Like with block A in the last slide, I'm going to exchange this force for mu sub s times a normal force, where the normal force is na on b. And that's it for this direction. Let's jump into the sum of forces in the y direction, which I think will give us a little bit more clarity, because here things are simple. We can move the weight of block B over to the other side, and now we know explicitly, hey, the normal force of block A acting on block B is just the weight of block B. And also, by Newton's third law, The normal force of block B acting on block A would also be equal to this value. But for now, let's take this value and plug it in over here on the left and see if we can't glean any useful information. So I've plugged in the weight of block B, and my next step is to exchange the weight of block B for mg, where we have the mass of block B times g. And this is great because now I have the mass of block B on both sides, and I can cancel it out, and now I have an explicit formula or expression, however you would like to call this, for the acceleration. And if you recall from the previous slide, there was also a tension. So we've knocked a couple variables down. We still have the tension to go. Let's move on to block C and see if we can't get anything useful there. Again, F equals ma at the top. Sum of forces in the x direction is 0 for block C because it's not even moving to the side. All it does is move up and down. So we can totally ignore that direction and go straight to the sum of forces in the y direction. So here we have the tension pointing in the plus y direction and the weight of block C pointing in the minus y, equal to minus ma, because the acceleration also points in the minus y direction. And what I'm going to do, like I said, I wanted to get something representing the tension, so I'm going to move this weight of block C over to the other side and isolate the tension. And perhaps one other thing we could do is exchange the weight of block C for mg, and now we have everything in terms of the tension that I think we'll need. Let's underline this as well, just to show that it's important, and incorporate that in the first equation that we underlined, this one here. So what I'm going to do is I'm going to plug in that expression that I just underlined for the tension in here. What I can do in this term is I can exchange the normal force of block B acting on block A with the weight of block B, because by Newton's third law, NB on A is the same as NA on B. They just point in opposite directions. The weight doesn't change, and we have the negative accounted for here, so we're free to do that. Also, we have an expression for the acceleration. So if we plug all that in, here's what it looks like. And remember, the whole goal is to solve for the mass of block C. So we can get rid of all the parentheses. We don't need them anymore. And furthermore, if you look at every term here, there's a G, a G, a G, and a G. Let's just divide them all out. So here's what we have left. And I want to get the mass of block C. So what I would recommend is taking this term here and moving it over to the other side. And now we are free on the left-hand side to factor out the mass of block C, which will look like this. And it's probably pretty apparent what we're going to do next, and that is divide both sides by what's inside the parentheses here, this 1 minus mu sub s. And I'm kind of running out of space on this particular slide, so let's go ahead and do that on the next slide here. And now we have an expression for the mass of block C in terms of everything that we know. And if we plug all of that in, here's what that looks like. And you should end up with exactly 39 as an answer. Exactly 39. Which makes me confident that we did exactly what we needed to do. And I believe that's our answer, and that should do it. That's it for this problem. Thank you for watching, and I wish you a safe and happy Labor Day holiday. Take care.